In this video, I will talk about the concept of work, and I will be using the definition of work. So this is defined as the path integral, and I will talk about that from the initial to the final position of the dot product of f dot dr. Now, first I'm going to talk a little bit about this idea. An integral is essentially an infinite sum. So one way to think about this is to say it's the limit when n goes to infinity of the sum I from 1 to n of the dot product between the force f sub I dot delta r sub I. Now, what does that mean? So if I have a point, let's say I have my system, it is here, and I know that there is a force acting on it. Let's say this is the force at this point, F1. Okay, so this is here at 1, and my this point particle is moving in this direction. The displacement is delta r1. Then to find the contribution to the work done by the force, I will calculate F1 dot product with delta r1. Okay, the force is a vector, delta r1, the displacement vector here, it is a vector. I can calculate the dot product and I will find the number, whatever that is. And then, since now my object has moved to this point, at this point there is going to be a different force acting on it because it has changed location. So now I call that F2. And the point will now be displaced, let's say, and it's going to go here, and this displacement vector is the delta r2. From this motion, I'm going to calculate the dot product between F2 and delta R2. And then the story keeps going. So now my object is here. The force acting at that point is this one. And now the particle goes here. Let's call that the delta R3. And now I calculate the dot product between this force and the displacement. And at the end of the day, when you have finished, when you actually have, let's use this, when we actually have, where is it going? Let's say the path, and this is the final point, this is here was the initial point. When we finish this process and we add everything, and when I say we add everything, I mean this, F1 dot delta R1 plus F2 dot delta R2 plus F3 dot delta R3 plus the rest of the dot products until you reach the final point. This is going to be the sum. This is going to be the sum over I of f sub I dot delta r sub I. Now, here is the thing. This calculation will become more accurate if I make the displacement vector delta r to be very small. In fact, the smaller it is, the more accurate my calculation will be for work. And that's why, since here I will have n such terms in the sum, the larger the n is, the more accurate this calculation will be, because the smaller the delta r, the smaller the displacements will be. Essentially, I'm dividing the path into a large number of segments. And for every segment, I'm calculating this dot product. Now, when I have this sum and I take the limit where the number of terms goes to infinity, essentially what this is that the path integral from the initial position to the final position of f dot dr. When you convert this to an integral, the delta becomes the d, because d shows that you have an infinitely small displacement. Okay, so this was an explanation of where we got why this is the path integral. It is a path integral because you need to follow the path. Now, how are we going to do that? I'm gonna talk about how we're gonna work with this integral. So I'm gonna copy the same thing here from the initial to the final f dot dr. Okay, this is, by the way, this is a definition of work. This will never give you the wrong result. There are other expressions out there that are valid when when the force is constant only, and of course those do have a limited applicability. They are only valid if you have a constant force. If your force is not constant, you have to use the definition, and I do recommend that you always start with a definition. If you see the force is constant, great, that makes your life easier, but I do recommend that you always start with this. You will never go wrong with this. Now, what do I do? Okay, so first of all, I'm not going to work with the path integral yet. I'm going to look at what I have inside the integral. I have the force vector and I have the dot product between that vector and the dr. So I'm going to write those vectors. Let's say f is fx, comma fy, comma fz. Okay, these are the three components. I'm not using any numbers. And in Cartesian coordinates, the vector dr will be simply dx, dy, dz. Okay, now this is a review. When you take the dot product between two vectors, this will be the sum of their x components. The sum, I just realized I have a typo here. So this would be y. What was I saying? So the dot product will be the sum of their x components. This with the dot product will be the sum of the product of the x components added to the product of the y components added to the product of the z components. So here it is, fx dx plus fy dy plus fz dz. Okay, that's how you calculate dot products. That's how we define this. So now the integral, essentially I can break this integral into 3 because I will have this inside the integral. So I'm gonna take this. Okay, let's take this and use it here, and this will be again the path integral from the initial to the final, fx dx plus fy dy plus fz dz. Now here's what I'm gonna do. This is a sum, and this is a sum inside this single integral. I'm gonna make this into a sum of 3 integrals. So this is gonna be the integral of fx dx plus the rest. Now here's the thing. This integral is going from the initial point to the final point, because this integral focuses only in the x direction. This is going to be my x initial, and that's going to be my x final. And here I will have fy dy, and that goes from y initial to y final, plus the same thing in the z, from z initial to z final, fz dz. Now, I'm not going to use specific numbers for fx and x initial and x final and so on, but if you have a problem where you're given the force and you're given the initial position and the final position, then you can do these calculations, and the sum of these three integrals will give you the work done by this force. It is important to remember, you need, by definition, you have a sum here of three integrals, x, y, z, if you happen to use Cartesian coordinates, but it is a sum of three integrals and you have to calculate all three. Now, what happens if your force is pointing in the positive x direction? In that case, you're lucky, Fy is 0, Fz is 0, because the force only has one non-zero component, the Fx. In that case, these two integrals are going to give you 0, so you only have to worry about 1. Now, one more comment. We do, so this is a sum of three integrals. If you happen to have, I want to make a connection with something else. If you happen to have a graph, let's say this is the fx and this is x, and you have the graph of what the force looks like. In when we use calculus, okay, we can calculate this integral, but if you want, you can also think of this integral. Okay, that's supposed to be a straight line. This area here, this is the integral from x initial to x final of fx dx. And let's say I'm gonna mark here, that's my x initial and that's the x final, just to make it clear. So if you if it makes your life easier to use calculus and find the integral, that's great. Go ahead and do that. There is another way. If you really like graphs and you like this representation, then you can plot your x component of the force along the x-axis, find the area under the graph, under the curve from x initial to x final, and that area is going to be essentially the same number as this integral. Okay, it's just another way to represent the same thing. This is with graphs. Here you would have to do the calculation using calculus.